Hello students, in this today's class we will read the summary of our chapter number 2. The chapter number 2 is electrostatic potential and capacitance, and in this chapter whatever we had read from the first topic, from the introduction to the last topic, we will just summarize and try to recall all these points for our better understanding. So when we started electrostatic potential and capacitance, the first thing which we were taught were the introduction to these static potentials and capacitance, where we have read about the forces and electrostatic, and then we have tried to understand what is electrostatic potential. So this electrostatic potential is denoted by V, and it is given for a system where there exists a charge and some charge which is brought from infinity to that particular point where the charge Q is existing. So the energy required to do so and the work required to do so under the electric field of this capital Q charge is termed as electrostatic potential. Then such a concept where only a single charge was in the system, we have derived formula by stating that we are deriving a potential due to a point charge. Then we received 3, 4, 5 and n number of charges, like this is Q1, Q2, Q3, Q4 and Q5. So when we have these many number of charges, it formed a system of charges, and we tried to find the potential due to system of charges. Then we introduced a dipole with charge plus Q and minus Q separated by a distance of 2a, and we defined potential in this case. Later on, after understanding potential for various conditions and considerations, we came to a point where we have seen that the two surfaces in our consideration are having the same potential, So when these two systems are there and we are bringing some test charge Q in this system, this test charge Q is undeflected and unbothered. This test charge do not feel anything, and we are not even providing external work to this charge in bringing it from surface 1 to surface 2 or vice versa. Why is it happening was our question. Then we understood that surface 1 and surface 2 have same potential, and these are termed as equipotential surfaces, and any charge moving in the equipotential surfaces do not feel any external force, and there is no requirement of external work to be done on it. After understanding the potential and equipotential, our aim was to define electric field and potentials relation. So in this case, we have taken a surface which is having electric field, and we defined potential for this surface, and then we related this V and E to find a relation between our potential and electric field, which is the root for the upcoming sections of our study. Once we know the relation between potential and energy, it is very much easy for us to relate the force, because force and electric field is related like this. It is very much easy for us to relate work with energy and potential energy with electric fields and so on. So just by introducing these two relation, it was became very much simple for us to make other relations. Then after discussing the potential, we came in terms to the potential energy. We defined potential for various systems. Then we started understanding what is potential energy. Then we read about potential energy for a charged system, and then for a system of charges, and for dipole, where we have introduced external electric field. Like this is a system, and in this system this is the charge present. This charge will not show any kind of potential energy because this is at a static point. Once we are introducing this external electric field in it, this charge will show the drifting and hence will attain some sort of potential energy, and hence we can calculate the potential energy. So to calculate potential energy, it is important as a factor to introduce external electric field. Then we read the various electrostatic properties of conductors. In these electrostatic properties of conductors, we read 6 set of properties, which when we will go to the next page, we will summarize, we will recall all. Then we read about the dielectrics and their polarization. First we read what is a dielectric, and then we understood how these dielectrics are being polarized. And then we started a very interesting topic, and the topic was of capacitors. First of all, we understood how these capacitors are made and for what these are made. Then we understood their basic property, that these capacitors have some capacitance. The energy they store is termed as their capability or the ability to hold that much. So that is the capacitance of the capacitor. Then in the most of the cases, we understood the property of capacitor using a parallel plate capacitor. So we introduced parallel plate capacitor. We understood how the parallel plate capacitor is formed and how that can be used to derive the various formulas and various properties of a capacitor. Later on, after understanding parallel plate capacitor, we get to know about series combination of capacitors and parallel combination of capacitors. In series, the capacitors are added like this in a single line, whereas when we said it's a parallel combination, we will draw parallel lines first of all, and then we will add capacitors to each parallel line. And this is a parallel connection, and all these will be connected to a single circuit. Here these all will also be connected to the circuit, but see, this is in a line and these are dividing the current over all the 4 pathways. And the last topic in the chapter number 2 which we studied was the energy stored in a capacitor. This is extremely useful topic, and for this topic only, to understand how this energy are being stored and how much energy is being stored in a capacitor, we have understood the whole working and construction of our capacitor. So in the last we have read about the energy stored in capacitor, and this energy was denoted with word U, and we have found that it is equals to the capacitance into the square of the voltage, half CV square. This potential energy in the capacitor was actually the work done to bring charge Q in the C1 and C2 having a potential of V, volts. So in this case we have found the work done, as our electric field is a conservative field, electric forces are conservative forces, so work done is also conservative in nature, and this is conserved in the form of potential energy inside the capacitor. So these are the topics which we have read under our chapter number 2, electrostatic potential and capacitance, and now we'll move on the summary and understand and recall all these topics. Point number 1 over here. Electrostatic force is a conservative force, work done by an external force equal and opposite to the electrostatic force in bringing a charge Q from the point R to point P is Q into Vp minus Vr, which is the difference in potential energy of the charge Q between the final and initial points. So in this statement we have defined the potential of our points. First of all, they have told us that force is a conservative force. As it's a conservative point, what we understand is that there is no losses. The force, if there is any loss, is stored in other form. So it's not been getting cancelled out or deleted from the system. There is only the exchange of this property into some other property. Now the work done in any system here is equal to the force but in opposite direction. So if force is done in this direction, work done is having the same magnitude but opposite direction. Why this is said so? Let's take 2 points. One is point P and other one is point Q. Or as stated in the question, we will take point R and point P for our better understanding and for not getting confused with the naming of the points. So this is our R, this is our P. At R we have to bring charge Q from P. At P we have a potential Vp and at R we have a potential Vr. So when we are bringing this Q from here to here, we have to travel from this potential to this potential. This potential of Vr can be repulsive and can be attractive. So when we are going from P to R, we need to do some work. Work is to be done. This work will be done against the force that is stopping the charge Q from moving from P to R. Need to provide external work which will help Q to overcome forces while moving from point P to R. So understand this, how much work we need to do is equal to the force but are in opposite direction. We do not need to do more than that work because our main motive over here is to bring the charge from P to R, nothing else. So we can define this work done as work done equals to charge, the charge which is actually supposed to move from point P to R, that into potential at P minus potential at R. So this will give us the amount of work that is needed to move the point charge Q from the point P to R. And from this, the potential is defined as work done per unit charge. Work done per unit charge. Now come to the point number 2. Potential at a point in the work done is the work done per unit charge, as already explained, by an external agency. Here the work is done by an external agency, not by the system. Okay, by external agency, because force is provided by the system. To overcome that force which is being provided by the system, externally we are doing some work in bringing a charge from infinity to that point P. Now we have thought that our charge is present at infinity and we are bringing it to this point P. For doing so, we need to provide some push to this charge. Like, just one example, one of your friend is not studying well, but you are studying well and you want your friend to get the same college as you are getting. So as you are very good at studies and you know that you will definitely land up in IIT, but for your friend's side you are not sure, but you wish to study with him, what will you do? You will try to push your friends into the studies. You will tell him various other profits you two will get if you two are in the same institute. How much fun you can have when you two both are in IIT. And then you can tell, like, if you join IIT there is better packages afterwards. So basically this is the external pushing to your friend to study well and get same score as you are getting, so you can both land up in IIT. So similar way we are also pushing this charge from infinity to come here to the point P. So this push is the external work. This push is the external work. Why we need to push is that because from this point P there is some potential that is producing force from the system. Why your friend doesn't want to study is that within him he don't know why he is studying, or he is distracted by other things. So similarly here this distraction is the force which is provided by this system, So the system's force we need to overcome and we need to provide work from external. Okay, so we are bringing by providing external work to the charge Q at infinity to point P. Since it is the potential difference between the 2 points which is physically significant. Between these 2 points, what makes the amount of work to drop and what makes amount of work to hype is the potential. More the potential, more work is needed to do. More V implies more work, more external work, and in case if V is less, then W external will also be less. So what is physically significant? It is the potential difference, not the force that is generated by the two charges and not the distance between them, but the potential difference. This potential difference takes into account other various factors which are there on the charge small q. Now if potential at infinity is chosen to be 0, potential at a point with position vector r due to the point charge q placed at the origin is given by this equation. Potential at point r equals to 1 upon 4 pi epsilon naught into q upon r. How come this formula came? See, we are having a charge this q, okay, and this is like we have chosen some origin, and at that some origin is present our capital Q charge. Our another charge is at some position at infinity. Okay, we assume that, this is our assumption, that at infinity V equals to 0, because it is very small. At a far away position the influence is very small, so that small influence can be regarded as 0 or null, 0 or null. Okay, and at potential, like at Q, there is some potential present. So we need to find the potential at position R. Potential at position R. Where is R? Now this charge is coming from infinity to this point. This point. Now this distance between the capital Q charge and small q charge is R. This distance is R. So we have to find what is the potential in this distance. To find so, we have potential equals to 1 upon 4 pi epsilon naught into potential will be generated due to capital Q. It will not be generated by small q. Potential will only be generated by the pre-existing charge in the system into capital Q divided by the distance between them. It is inversely proportional to the distance. Whereas our electric field and force are inversely proportional to the square of distance, but our potential is inversely proportional to the distance. So this is the formula by which we define potential at a distance of r centimeter away from our pre-existing charge in the system. Now the third point, the electrostatic potential at a point with position vector r due to the point dipole of dipole moment P placed at the origin is this. Understand now? Now we are talking about the dipole. Now we are talking about the dipole. What is a dipole? Dipole is a system of two charges. Both the charges have same magnitude but different polarity and are separated by a distance of 2a. The dipole moment for this system is given as, dipole moment P is given as 2aq. 2aq. In this system also there exists a potential. In this system of q and minus q, in this system of potential, there exists in this system of dipole there exists a potential, and that is denoted by V, and we have to find, like this is our dipole over here, 2a plus q minus q, and we brought a charge q over here. So this is the distance from the dipole r. Okay, this is distance from our dipole to this test charge q, that is r. I'll make one clear diagram so that it will give you a better understanding. This is our dipole plus q minus q. Length of dipole is 2a. Now this test charge q is coming from position infinity to position r. To position r from the center of dipole. From the center of dipole. We always measure distance from the center of dipole. Okay. So now what is the potential? We know that potential equals to 1 upon 4 pi epsilon naught into the charge by the distance between them. Now this charge can be defined with respect to the dipole moment of our dipole. So when we define this charge with respect to the dipole moment, we get to know that V at R, like from the center to QT is equals to 1 upon 4 pi epsilon naught into dipole moment upon r square, dipole moment upon r square, and that is multiplied by r bar. So r cap, this r cap denotes the unit vector of position. This unit vector of position provides us the direction from the dipole to QT. Provides the direction. We have already read a unit vector is usually used to understand or to define the direction of the system. So the result is true also for a dipole which charges minus q and plus q separated by a distance 2a for when r is much bigger than a. Like if this r here, see the follow up the red ink, if this QT is placed at a distance this, here we see that r is much bigger than a. See, a is only this much, maybe 6 mm, or you can say 0.6 centimeter, and see how much is this distance. This is approximately 9 to 10 centimeter away. So see the difference in the distance, it is far away. So when this case comes where r is way too bigger than the a, in such situation also this particular formula follows up. We do not assume this system of small dipole to be equal to a point charge. In few cases what we do, if a dipole is extremely small, we assume that this is not a dipole but a charged configuration. But when we read potential, this dipole will be considered as dipole, let it be any small or any big, that doesn't make any difference. Coming to the fourth point, potential for a charge configuration q1, q2 up to qn with position vector r1, r2 up to rn, the potential P is given by superposition principle. That is equals to V equals to 1 upon 4 pi epsilon naught into q1 upon r1p plus q2 upon r2p up to qn upon rnp. Here r1p is the distance between q1 and p and so on. See, this is the statement where we have tried to find potential for a system of charges. In this system of charges, we have many charges q1, q2, q3, q4 and like that many like qn, and this is our point P where we have brought the charge qt. I am using this charge qt to define it as a test charge which we are bringing from the infinity to the decided point, so that we can understand the value of potential at that, to understand the value of potential. So from this point r1's distance is, from this point distance of q1 is r1p, distance between charge number 1 and point P. Similarly, this distance is r2p, this distance is r3p, this distance is r4p, and from n it is rnp. For one charge, potential is written as, like for charge q1, potential can be written as k into q1 upon r1p. Here mention that k equals to 1 upon 4 pi epsilon naught. So in this entire lecture I will use k for this particular dimension. I will not write the whole, it will save a little of our time. Similarly, for Q2 potential can be written as K Q2 upon R2P, and similar way for VQ3, VQ4 and VQN. So VQN can be written as KQN upon RNP. Now when we use a superposition principle, using superposition principle, the total potential of the system turns out to be V1 plus V2 plus V3 up to Vn. So see here, this is our value of K, this is for V1, V2 and this is for Vn. When we added up, we got this total potential, and these are the charges and this is the distance between our point P and our charge number 1, 2, 3, 4, N respectively. Coming to the fifth point, an equipotential surface is a surface over which potential has a constant value. Important line. For a point charge, concentric spheres centered at a location of charge are equipotential surfaces. See, I'll explain this second one. We have concentric circles like this. This is our point charge Q. This will have this one concentric circle, other concentric circle, third concentric circle. Okay, the distance between this and this point is R. Distance from this to this point is P, and distance from this to this point is Q. Now see, our potential, one second, I'll rub this space. Our potential is given as V equals to K into Q upon R. So potential is either dependent upon the charge or dependent upon the distance. But in this case, our charge is same. Charge equals to same. What is different? In this circle, in this circle, our R is also not different. But in this circle, radius increased, and in this circle, radius increased further. So what I aim at saying is that for this one circle, there will be one potential V1. For this second circle, there will be another potential V2, and for the third circle, there will be another potential V3. But throughout this entire surface of circle 1, we will have same potential. Throughout circle number 2, we will have same potential, because in these concentric circles, neither Q nor R is changing. They both are same. But when we see potential at 3, which is smaller than the potential at 2, and that is smaller than the potential at 1, because potential is inversely proportional to our R, and when we go from one surface to 2, 2 to 3, our R is the only thing which is decreasing. R is decreasing. Okay. Electric field E at a point is perpendicular to the equipotential surfaces through the point. Here this electric field will be given like this, perpendicular to the surface. Just think, this is our surface and something going at a 90 degree from this surface. Okay, take a plate. On the surface of plate, stand your pen. How they will look? They will look like a equipotential surface having a perpendicular electric field line. Okay, so electric field lines are perpendicular to these equipotential surfaces, and E in the direction of steepest decreases with the potential. So here the line that electric field at a point is perpendicular to equipotential surface will be given like this, and the other statement which says that electric field is in the direction of steepest decrease of potential. This line is quite important to understand. See, the potential, work, force, all these three things are related to each other. Basically what happens is that for a given system we have a work done. This work is done against the force that is provided by the system, against the force, and from this work done we derive the formula for the potential. So potential and work done are in the opposite direction. Now this force is related directly to the electric field. Hence when we relate potential and electric field, what happens is that potential decreases in the direction of electric field, where the electric field increases, our potential decreases. For this we have read the relation between potential and the electric field. Relation between electric and potential field. So we will just see what was the relation within a single line, and we'll move to the next point then. See, we'll consider the two equipotential surfaces, one with a potential of V and other with a potential of del V. One with potential V and other one with a potential of del V, to understand this relation of E and V. Now we are bringing a charge Q in these two systems. This is V plus del V, okay, not just del V. The difference between these two potential is this. So we are bringing a charge in this. We need to do some work. That amount of work done will be written as W equals to Q into V minus del V into V, okay, del V plus V. That is the amount of work done given in a simple statement. Now as this is the potential difference, and this difference can be defined on the basis of electric field also. This will be equal to our electric field. Just come to the right below corner, E del L, and which is equals to V minus V plus del V. This will give us the value of only minus del V. This is in a bracket, okay, this is one unit, this is another unit. So we will receive only this much amount. This is again equal to the work done. Now we will find E from here. E will be E equals to minus of dV upon dl, okay. This is the amount of electric field. Now as we want to change this sign, we will take the mode of dV. If we take the mode of dV, the negative sign will be resolved. So we will get it as dV upon dl. Later on this dV and dl can be integrated like this. See, del V equals to E del L, okay, and we did not introduce a mode. In such case we will integrate this, what we will get is V minus V equals to E integrated over dl, okay. So our potential will be given as V equals to minus E dl. So this dl can be integrated on the basis of the distance we are taking between the two potential surfaces. So here we have this case when the test charge is positive, when this test charge which we are bringing, this Qt, is positive. In this case the potential gradient will be more near the charge. Near the charge, potential gradient will be more. In case the test charge is negative, potential gradient will be more as we move away from the test charge. And for the equipotential surfaces, the potential at every point of the surface will be same. Thus, there is no potential gradient, or the potential gradient is going to be 0. This is what this statement E is in the direction of the steepest decrease of the potential says. Because see here, V and E are negatively proportional to each other. Negatively proportional to each other. Now, we'll move to the sixth point. Potential energy stored in a system of charges is the work done by an external agency in assembling the charges at their location. Potential energy of two charges Q1 and Q2 at R1 and R2 is given by U equals to 1 by 4 pi epsilon naught into Q1 Q2 by R12. R12 is the distance between Q1 and Q2. Here we are defining the potential energy for a system of charges. In this system of charges, we have taken only two charges. We can have 3 charges, 4 charges, or n number of charges, and all these will be kept in a particular configuration. So how these can be kept and how the potential energy can be found out, we'll see. See, when this charges is Q1 over here and Q2 over here, the distance between them is defined as R12. This is two charge system. Now we have 3 charges. They will form a triangle like structure. Okay, when we close all the 3 charges, it will form a triangle like structure, Q1, Q2, and this is Q3. So this distance will be defined as R13, this as R12, and this as R23. So we will find like energy in this particular system first, then in this system, and then in the third system. So energy by the principle of superposition will be given as potential energy in system 1 plus potential energy in system 2 plus potential energy in system 3. Similarly, when we have 4 charges, they will form something like a square, rectangle, parallelogram. So we will say the 4 charges will form quadrilateral with the distance 1, 2, Q1, Q2, Q3, and this is Q4. This will be R23, R34, R43, and then with respect to this and this also we have to find. This will be R13 and R24. So now energy provided to 1 due to 2, energy provided due to 3 at 1 due to 4. This will get added up to find the total energy. Then energy provided by the 2 for 3 by 2 for 4, then energy at 3 and 4 between 3 and 4, and then energy at 4 only. So this will give us the total energy. We have to sum up this energy, this, and then in the diagonal, by the diagonal factor, what all energies are coming. So we will use superposition principle in this. And while we were understanding this topic in our chapter 2, we have solved 2 to 3 problems related to this. Like when we are bringing the charge 1 into the system, there is no differences because charge 1 do not have any competition in this system. There is no charges available at the 3 corners. So the work done to bring the first charge will be 0. When we are bringing the charge 2, there is a charge 1. So work done will be with respect to Q1. When we are bringing Q3, the charge with respect to Q1 and Q2 will be like work will be done with respect to charges 1 and 2, and so on. If we are bringing n charges, before that how many charges are present, they all will contribute to the work done. See over here, the potential energy of a charge Q in the external potential V is given by QVR. Work done when potential is external will be equals to charge into potential at point R. Okay. The potential energy of a dipole moment in a uniform electric field is given as this. the potential in the uniform electric field. Now our electric field is external in nature. We are dealing with external electric fields, right? E external. So V is given for that. But now we have introduced one more condition, and that condition is our E external is uniform in nature. Uniform in nature. In that case, our potential will be given for a dipole as minus P into E. This minus is contributed from the electric field, as we have seen in the previous point where we have related the potential with electric field. Coming to the 8th point, electrostatic field E is 0 in the interior of a conductor. Just outside the surface of charged conductor, E is normal to the surface, given by E equals to sigma upon epsilon naught into n cap, where n cap is the unit vector alone, the outward normal of the surface, and sigma is the surface charge density. Charges in a conductor can reside only at its surface. Potential is constant within and on the surface of conductor. In a cavity within the conductor with no charges, electric field is 0, which is termed as electrostatic shielding. So these all properties what I have read so far comes under the electrostatic properties of conductor. Electrostatic properties of conductor. Okay. So in these electrostatic properties of conductor, we have 6 properties which I have read for you. I'll make the point at the below corner, just see it so that we'll have a clear-cut explanation in that format. So it will be easier for you to understand. As this is a paragraph, we'll just divide this paragraph into the point system. Now see. First property of our conductors when we deal with the electrostatics is that inside a conductor E is 0, electric field is 0 inside a conductor. E equals to 0. Why so? Because in a conductor we have many charges flowing here and there. These charges, when they flow here and there, they have some kinetic energy, but all these charges have a total kinetic energy of 0. There is no force among each other. Like this is a system, these are the charges and they play with each other a lot. But when we see this overall conductor, between these two there will be a electric field generation, there will be a force, there will be a potential. But when we see this as a system, in this whole system the overall force is 0. So these charges when we see from outside seems to be static, not in motion. So when this electric field is provided from outside, for a moment, for a split second, there will be the changes, but after that split second these charges will acquire a position at which the electric field will tend to 0. There will not be any more motion. These charges will acquire the equilibrium state. Though they will not stay static as such, they will have the movement, but overall movement will be named as static. Therefore, this electric field inside the conductor is always 0. Now the second one states that this second and third statement is very much related to the result of our one statement. This one statement tends to give 2 and 3. At surface, electric field is normal to surface. At surface, if we see, E is normal to surface. This is our surface and this is the direction of E. This is radius of the surface. So see how much angle they are making, 90 degree. So these are normal. This is E. And this will happen always. Always for a conductor surface, electric field is at 90 degrees at normal position. Now the third point. Interior of conductor can't have excess charges in the static situation. Interior of conductor equals to no excess charges in it. Why so? Because electric field is zero. There is no force of drift. So these charges, now like overall as a system tends to be static, and when we try to introduce a charge in this conductor, this is repelled out due to interatomic or internuclear interactions. So these electrons and the protons which are residing in this conductor, these charges will have their own attraction and repulsion, and whatever new charge we are introducing in system will be repelled. Hence they will not have any excess charge in the interior of conductor. As the space over here is preoccupied, we'll just move to this corner after explaining the point number 4. Electrostatic potential is constant. Electrostatic potential V is constant inside and on the surface of our conductor. It is same. If we are inside the conductor, we have same potential. On the surface also we have same potential. How come that is happening? That is happening because like the potential is related to electric field as EDL. So E is 0. E is 0. When E is 0, the potential becomes potential becomes constant, and similarly when E tends to be again E, it do not affect our potential and potential remains same. So when we see inside of the conductor, potential is EK upon R, and when we see on this surface, potential is KQ upon R. So throughout this system from R equals to 0 to R equals to R, potential remains same. Now the fifth point, E at surface of a charged conductor is given by, electric field on a surface is given by sigma upon epsilon naught into n cap. So sigma, this electric field is related with the surface charge density upon the permittivity. Surface charged density upon permittivity. So electric field is given as surface charge density divided by permittivity into n bar, and this n bar gives us the unit vector. Now sixth point is of electrostatic shielding, which is extremely important. When we are having a conductor, in this conductor we have a cavity. Now to this conductor we have provided a lot of charge. This charge will start distributing at the surface because no excess charge can reside inside the conductor. So they will not move inside the conductor but will reside on the surface of conductor. When this is not happening, do you think the charge will come to this point? No, the charge will not come to this point. So this cavity will remain uncharged. When this cavity is uncharged, what will happen? There will not be any electric field or any potential inside this cavity. So this cavity is shielded from the electric current. So this kind of concept we use in our instruments. Like if we are inside a conducting cavity, we will not feel any electric charge. Just think we are having a conductor, okay? Inside this conductor there is a cavity, and from this we are providing electric currents. We are moving in this conductor. So do we feel any kind of electric shock? No, because due to this electrostatic shield, because electrostatic shield implies when electrons or the charges inside the conductor are at static position, they repels the extra charge. When extra charge is not imparted inside the conductor, they cannot move to the end of the cavity, and if they are not moving at the end of cavity, there is no generation of electric field. And when there is no generation of electric field, anybody or anything inside this electric cavity will not feel any electric current. So we will be shielded. So this is very much important concept in designing many electrical instruments. So these are the properties of conductor. Coming to the 9th point over here, a capacitor is a system of two conductors like two conductors are placed nearer to each other, or we can say that a capacitor is a system of two conductors separated by a insulator. So like this is our conductor 1 and this is our conductor 2, they are kept near to each other. In between them is air. Air works as an insulator. So this system is called capacitor. Its capacitance is defined by C equals to Q upon V, that is charge by potential across the two conducting surfaces, Q like C1 and C2, where Q and minus Q are the charges on the two conductors. If this conductor is having a charge Q, this conductor must have a charge minus Q. So the charge on the conductor 1 and conductor 2 should have magnitude equal, but there can be a difference in the polarity of the charges, okay? Now potential V is V is the potential difference between the two conductors C1 and C2. C, capacitance C is defined purely on the basis of geometry or shape, size and relative position of two conductors. Shape, size and relative position of two conductors. The unit of capacitance is 1 farad or the farad. Farad is given as coulomb per volt. Coulomb per volt. Why do we say that capacitance is dependent only and only on the geometry, shape, size and relative position of conductors? Because C equals to Q upon V is a constant. Here C is written as epsilon naught A upon D also. A over here is area, and area of a square will be different than the area of a rectangle and will be different of area of square. So area of any shape is different. So as the shape changes, area will change and hence the capacitance will change. D is the distance between the two capacitor plates or the two conductors. Distance between C1 and C2. So this distance can be nearer, like just 1 centimeter away, and it can be like very far, 30 centimeters away, or maybe 1 kilometer away. So as this distance, this separation increases or decreases, will decrease or increase the capacitor. How? See, capacitor is directly proportional to the area of C1 and C2. conductor plate 1 and conductor plate 2. So if area is increasing, C will increase, but in case of the distance between them, C is inversely proportional to the D. So in case D is increasing, our C will increase. This is the relation between the shape, size and relative distance between the conducting plates. Now for a parallel plate capacitor, we are assuming that our conductors are plate. They can be rectangular plate or they can be circular plate, and these are parallel to each other. That implies like this, parallel. They are having some distance between them and they are parallel. Just keep your both hands together facing each other. That is the parallel state. Okay. And this is the another plate, and these are also parallel. The shape can be anything, but both the plates are having same shape, and from above to below they are separated by the same distance. That is a parallel plate capacitor, and with vacuum in between them. In between them is the air. In this they have air. Vacuum simply implies it's either air or nothing. Okay, so they have air here between the plates. So that in this case the capacitance is given by epsilon naught into A by D. Here A is the area of each plate and D is the separation between them. 10th point, if the medium between the plates of capacitor is filled with an insulating substance, that is a dielectric, the electric field due to the charged plates induces net dipole moment in the dielectric. This effect is called polarization and gives rise to the field in the opposite direction. The net electric field inside the dielectric and hence the potential difference between the plates is thus reduced. E net reduced and V reduced. Consequently, the capacitance C is increased from its value C naught, where there is no medium in the vacuum. C equals to K C naught. K over here is a constant, and that is a dielectric constant of the insulating material or insulating substance. Now understanding it, we had our capacitance plates over here named as C1 and C2. Our one formula is C equals to Q upon V, where C depends upon the charge and the potential, and the other formula is C equals to epsilon naught A upon D, where C depends upon the area and the distance between the two conducting plates. Now in this C1 and C2 we have introduced a dielectric. What is a dielectric? It's a insulating substance. It's a insulating substance. Dielectric equals to insulating substance. This insulating substance do not allow the passage of electric fields. Now what happens to this insulating substance is that here we have positive charge. Due to this positive charge we have a surface charge density which is positive in nature, and here we have negative charge. Due to this a negative surface charge density is introduced. This is dielectric. Due to these positive charge we have induction of negative charges on this surface, and due to these negative charge we have induction of positive charge on this surface. Now see, we have a surface where we have positive charge and negative charge, then we have a surface where we have positive charge and negative charge. Initially we had only positive charges in the conductor plate 1 and negative charges in the conductor plate 2. So the electric field was in this direction. Now inside the dielectric, electric field is like this, and outside the dielectric, electric field is like this. I will write over here, electric field of plate 1 and plate 2 is from positive to negative, whereas electric field when we introduced a dielectric is in the opposite direction, in the opposite direction. Okay, so the whole direction is reduced. Now when we will sum up this electric field, summed electric field will be EC1 C2 plus E dielectric. So dielectric is having a negative value, so the sum E will be lesser, summed E will be lesser. As we know, the relation between E external and voltage is this V dl, right? V upon dl. So in this case, what will happen, as electric field increases or decreases, will ultimately increase or decrease the potential also. So when the electric field is lessened down, our potential also get less. When potential is getting lesser down, from this particular equation we find that our capacitance increases. Okay, so when we introduce a dielectric in the system of capacitors, the capacitance of these two capacitors increases. So introduction of dielectric inside the capacitor is a helpful way for us, and due to that our voltage also, potential also decreases. So when we have this system of capacitors and we are providing some voltage, like your phone, okay, your phone is there, inside your phone's battery we have capacitor, because capacitor is used for storing the energy. This battery which you store and use up as 24 hours or 36 hours of your work with the phone without charging is coming from these capacitors. So now this capacitor stored your energy, but these capacitors need a lots of amount of voltage. In generally, the voltage coming to your home is 220 AC voltage, but if we do not introduce a dielectric in between C1 and C2, what will happen? This will not be sufficient for charging our mobile phone. We may need 500 voltage, 600 voltage, which may damage our electrical equipment. So what we do, we introduce dielectric between our capacitor plates. Due to that, just 20 voltage is enough, 50 voltage is enough. Just go and check the charger of your phone. They have mentioned that on your charger we just need 120 voltage to charge this phone. So that is how we are reducing the input of voltage in our system. So due to less potential that is being generated in the circuit, we can charge our capacitor more efficiently, and this happens just because we are introducing a dielectric. And here in the equation, C equals to Kc naught, K is a dielectric constant of this insulating material. More the dielectric constant, more the capacitance. Less the dielectric constant, less is the capacitance. It is directly proportional. Now we will see capacitor which are arranged in series combination and capacitor which are arranged in parallel combination. When capacitors are connected in series, they are given as 1 upon C equals to C1 plus C2 plus 1 upon C3 and so on. Why so? This comes from this particular equation, C equals to Q upon V, V equals to Q upon C, okay, C. Now when these are in this system series connection, see, this is our series connection. In this series connection, the voltage across the capacitor changes. Voltage will be V1, V2, V3, V4 and so on. But what about the charge? I is not getting distributed. From electric current only we are deriving the electric charge, okay. So current is not changing, so the charge over here will remain same, Q, 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 Q. This is our C1, C2, C3 and C4, so on, okay. So Q is remaining same, only V1, V2, V3 is changing. So V1 can be defined as Q upon C1, V2 can be defined as Q upon C2, so on up to Vn, which can be defined as Q upon Cn, okay. So when we want to find the total potential across all the capacitors from C1 to Cn, what we will do, we will add up this potential. The total potential will be given by V1 plus V2 up to Vn. and this will be given as Q upon C1 plus Q upon C2 plus Q upon C3 up to Q upon Cn. Then here Q will be like removed from this system. We will get what is the value of what is the value of this V. This V can be written as Q upon the combination of all the capacitor in the series. So it will be Q upon combination of all the capacitor in the series equals to Q into 1 upon C1 plus 1 upon C2 up to 1 upon Cn, and this Q and this Q will cancel out, giving us a result 1 upon Cs equals to 1 upon C1 plus 1 upon C2 up to 1 upon Cn. See, this is what we have got for the series connection. Now we have our capacitors in the parallel connection. So parallel connections are made like this. Okay, and now this charge is coming from here I, and this charge coming out from here is also I, but according to Kirchhoff's law, when this I goes at this junction, it will be as I1, and here it will be only I2, here it will be I3, and going up it will remain only I2 minus I3. Here the current will distribute, making the charge also distributed. Current will be distributed, hence Q will also get distributed as Q1, Q2 dash 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 Qn, but voltage or the potential will remain same throughout the system, V. Now we know that C equals to Q upon V. Here we want Q1, Q2, Q3. So Q1 will be C1V, Q2 will be C2V, Q3 will be C3V, and so on up to Qn, which will be equals to Cnv. Now Q total will be given as Q1 plus Q2 up to Qn. So Q total can be written as V, like potential into capacitors in the parallel combination, which is equal to C1 into V, C2 into V up to Cn into V. Now this V is common and same, so we will cancel out from each step and we will be left with Cp. Capacitors in parallel combination equals to C1 plus C2 plus C3 up to Cn. See, this is what we have got for the parallel combination of capacitors. C equals to C1, C2, C3 up to Cn. Here C1, C2, C3 are the individual capacitors, both in series as well as in parallel combination. Now we will read energy U stored in capacitor of capacitance C with charge Q and voltage V, that is given by U equals to half QV, which is equals to half CV square, and that in turn is equals to half Q square by C, and the electric energy density is energy per unit volume in a region with electric field is equals to half epsilon naught into E square. We will just simply go and see the derivation for this one step so that we will get a better understanding. So see over here, like we have two plates of capacitor, they have their own amount of charges on them. Now we introduce a small charge del Q in the plates. To bring this del Q from this point to this point, we will need to do some work because it is going against the potential. So that work done will be a small work done because our charge is small. So small work done. dW equals to dQ, like dQ into the potential. That is what we know. This potential can be written as dW equals to, as we know, potential can be written as V equals to Q upon C. Okay, so we'll write it here, Q upon C in del Q. We will integrate this and we will get W equals to, after integrating, okay, 1 upon C into Q square upon 2, that is after integrating. In the first point itself, we have understood that all these systems are conservative in nature, therefore this work done will be conserved in the system as potential energy U. So potential energy comes to be half Q square upon C. So that's how the potential energy is derived, and by using this particular formula we can write potential energy in these three varied forms. Hope you understand this. So this is the whole summary of our chapter number 2, where we have read so many topics, and these so many topics are again being recalled, and few derivations which are important are derived on the board here in this summary part also, as well as when I was explaining these topics in the previous concept, it was explained there also. So we'll move next to the dimensions. We will understand and read few dimensions too. So see the physical quantity potential. Potential is denoted with a symbol of V, but potential can be denoted with this symbol, and this symbol is known as psi. Okay, and this potential have a dimension of m1 L2 t to the t minus 3 a minus 1. Here m denotes the mass, L denotes the length, t denotes the time, and a denotes the current or charge. Unit of this potential is V, volt. Potential difference is a physically significant quantity. Always remember, this is very much important. Potential is a significant physically, and that's why we need to define potential. Once we define potential and relation of potential with work done, force, electric field, we can define all these quantities very nicely. So it is a physically significant quantity. Then we have capacitance. Capacitance is basically written as Q upon V, and it is a constant which defines a capacitor. This is denoted by a symbol of capital C, and here the dimensional formula is m minus 1 L minus 2 t minus 4 a2, and the unit for this is F. What is F? F is farad. Farad in the form of charge and voltage can be written as coulomb per volt. Coulomb per volt. Next is polarization. Polarization is given by small p with a vector form. So polarization is a vector quantity, and dimensionally it is written as L minus 2 AT. Its unit is coulomb per meter square. Coulomb per meter square. It is dipole moment per unit volume. Dipole moment per unit volume P. This is P is dipole moment by V, volume, dipole moment. So this P is capital and this is small p, which defines our polarization. As our moment, dipole moment is a vector, so this unit of polarization is also a vector. Next is dielectric constant. This dielectric constant is defined for dielectrics. What are these dielectric? These are the insulators which are introduced between the capacitor plate C1 and C2 for increasing their capacitance. Dielectric constant is denoted by capital K. It is a dimensionless unit because this is written as C equals to Kc naught, initial capacitance, final capacitance. So K equals to C upon C naught. What is the unit of C? It is farad. What will be the unit of C naught? Same, farad. Farad will cancel out. What is the unit over here then? No unit. So it is a dimensionless and it doesn't have any unit. No unit. Okay, these are the four new topics or the four new terms we got introduced with. So it is a little necessary for us to recall these points on the basis of their symbols, dimensions and units. So that's all in the class of summary. We'll just see few more points in the next class related to our chapter number 2. So have a good day and study well. Bye bye.